One minute, you're driving down a clear, sunny highway. The next, you can't see the hood of your own car. You've just hit a wall, a sudden, blinding wall of white. This isn't a blizzard. It's something faster, more sudden, and in many ways far more dangerous. We're about to dive into the wild and unpredictable world of the snow squall.
If you're fascinated by the raw power of nature and the planet's most extreme weather, you're in the right place. Go ahead and hit that like button and make sure you're subscribed so you don't miss a single fact. Let's start with what a snow squall actually is, because it's one of the most misunderstood weather events out there.
It's not a storm that settles in for a day or two. It's a meteorological ambush. A true snow squall is defined as an intense but very short-lived burst of heavy snowfall. This isn't just a few pretty flakes. We're talking about snowfall rates that can reach 2, 3, or even more inches per hour. But the snow is only part of the story. These events are almost always accompanied by strong, gusty winds, often exceeding 30 or 40 miles per hour. This combination of heavy, wind-driven snow is what creates the infamous whiteout conditions. To make matters worse, a squall brings a shocking and rapid drop in temperature. It's not uncommon for the thermometer to plunge 10 or 20 degrees Fahrenheit in just a matter of minutes as the squall line passes over, flash freezing any wet surfaces. But what truly sets a squall apart from its winter cousins isn't just its intensity, but its incredible speed and suddenness. A classic blizzard is a long-duration event defined by sustained conditions lasting for hours. A snow squall is the complete opposite. It's all about the shock factor. The transition from perfectly clear skies to a complete whiteout can happen in less than 5 minutes. Imagine driving with miles of visibility and then, with almost no warning, being plunged into a chaotic swirl where you can barely see a few feet in front of you. This is the signature of the squall. Their duration is also remarkably brief. While they feel like an eternity when you're caught in one, most snow squalls last for less than an hour, and many pass over a specific location in just 15 to 30 minutes. Then, almost as quickly as it began, the sun can reappear, the winds can calm, and the sky can turn blue again, leaving behind a fresh, dangerous coating of snow and ice. This rapid-fire hit-and-run nature is precisely what makes them so hazardous. To understand how something so violent can materialize from a seemingly calm sky, we have to look at the volatile recipe that creates them. At its core, a snow squall is a product of atmospheric instability, much like a summer thunderstorm. They typically form when a mass of very cold Arctic air flows over a relatively warmer surface. This could be the unfrozen water of a large lake, or it can even be just moist ground that has been warmed by the sun. The temperature difference between the cold air above and the warmer surface below creates convection. Think of it like a pot of water on a stove. The warm, moist air at the surface rises rapidly, and as it ascends into the cold air, its moisture condenses and freezes, forming immense amounts of snow crystals in turbulent updrafts. This process happens incredibly fast, building the squall's towering cloud structure in a short amount of time. Many of the most powerful squalls form along the leading edge of an Arctic cold front, where the clash between the advancing cold air and the warmer air it's displacing is most dramatic. When that atmospheric pot boils over, the result on the ground is where the real, immediate danger lies. The number one threat from a snow squall is the instantaneous loss of visibility, particularly for transportation. On a highway, a multi-lane stretch of road can go from clear to zero visibility in the time it takes a car to travel a quarter mile. Drivers who were just moments before cruising at full speed suddenly find themselves completely blind, with no reference for the lane, the shoulder, or the cars right in front of them. This is the scenario that leads to catastrophic chain reaction pileups, sometimes involving dozens or even hundreds of vehicles. Compounding this is the flash freeze. The rapid temperature drop instantly turns any wet pavement into a sheet of black ice, eliminating traction just as drivers need it most. The snow itself accumulates so rapidly that road crews simply can't keep up. The danger isn't the total amount of snow that falls, but the sheer rate at which it comes down, creating treacherous conditions in the blink of an eye. Have you ever been caught driving in a sudden weather event that appeared out of nowhere? It can be a terrifying experience, and I'd be interested to hear about it in the comments. Interestingly, not all of these white walls are born from the same conditions. Meteorologists generally classify them into two main families: lake effect squalls and frontal squalls. Lake effect squalls are legendary in regions downwind of large bodies of water, like North America's Great Lakes. As frigid winter air from Canada sweeps across the relatively warm, open waters of the lakes, it absorbs massive amounts of moisture and heat. When this modified air mass hits the colder land on the other side, it's forced to rise, dumping that moisture as incredibly intense, localized bands of snow. These bands can be persistent, staying over one area for hours and dropping feet of snow. Frontal squalls, on the other hand, are more nomadic. They can occur anywhere and are associated with the sharp leading edge of a cold front. They are typically more organized and move progressively across the landscape, not lingering in one spot. While lake effect events produce higher snow totals, frontal squalls are often considered more dangerous because they can strike in areas unaccustomed to such sudden, extreme winter weather. Whether they're born from a lake or a front, these squalls often share a fascinating and formidable structure. They frequently organize themselves into a squall line, which is a long, narrow band of heavy precipitation. This line can stretch for hundreds of miles, yet be only a few miles wide. Visually, it can appear as a dark, ominous, and turbulent wall of cloud approaching on the horizon. From a satellite's perspective, these squall lines look like sharp, white ropes being dragged across the landscape. The weather on either side of this thin line can be drastically different. Ahead of it might be sunshine and calm winds, while directly behind it, the heavy snow has already stopped and the sky is beginning to clear. This incredibly sharp gradient is why the change in conditions is so abrupt. You're not gradually entering a storm system, you're crossing a distinct, fast-moving boundary into a zone of meteorological chaos. The winds ahead of and within the squall line are also highly organized, creating a gust front that hits just before the snow arrives. Because of this unique, fast-moving structure and the sheer danger it poses, weather forecasting agencies had to completely rethink how they alert the public. For years, the rapid and localized nature of snow squalls made them fall through the cracks of the warning system. A broad winter weather advisory didn't adequately convey the immediate, life-threatening danger of a sudden whiteout on a highway. In response, the U.S. National Weather Service introduced a new high-priority alert in 2018, the Snow Squall Warning. This warning is issued as a wireless emergency alert, pushed directly to smartphones in a specific, targeted geographic area, the same system used for tornado warnings and flash flood warnings. The goal is to give people, especially drivers, a crucial 15 to 30-minute heads up to delay travel or exit the highway before the squall hits. This change in protocol officially recognizes the snow squall as an event with the same potential for imminent danger as a tornado, highlighting just how seriously this phenomenon is now taken by meteorologists. It's a modern solution for a problem that has plagued travelers for centuries, a problem born from the sky's ability to unleash winter's full fury in a matter of moments. But what happens inside these squalls, at the microscopic level where the snowflakes themselves are formed? The answer is more complex and violent than you might imagine. What we're looking at isn't just a storm, it's a meticulously planned atmospheric assault. The term snow squall itself hints at this violence, but the reality is far more precise. A true snow squall is a meteorological ambush defined by a trinity of sudden, extreme conditions. First is the incredibly intense yet short-lived burst of heavy snow. We're not talking about a gentle flurry that builds over hours. This is a blinding curtain of snow that drops from the sky with shocking speed, often accumulating several inches in under an hour. Accompanying this is the second element: powerful, gusty winds. These aren't just steady breezes. They are chaotic, turbulent winds that can whip the falling snow sideways, creating a swirling vortex of white. And the third, most dangerous component is the catastrophic drop in visibility. In the span of just a few minutes, visibility can plunge from miles to mere feet, sometimes even to absolute zero. It's this combination, the suddenness, the intensity, and the blinding nature, that officially makes a snow squall one of winter's most treacherous and effective predators. It arrives without warning, unleashes its full fury, and then, often just as quickly, it moves on, leaving chaos in its wake. But the snow and wind are only part of the trap. The real secret weapon of a snow squall, the one that causes so many accidents, is the flash freeze. Imagine driving on a road that's merely wet from melting snow or a brief moment of sun. As the squall's leading edge, known as an Arctic front, sweeps through, the temperature can plummet with breathtaking speed, often dropping 10 to 20 degrees Fahrenheit or more in a matter of minutes. This isn't a gradual cooling, it's a thermal shockwave. Any liquid water on the pavement doesn't just freeze, it instantly crystallizes into a treacherous, often invisible layer of black ice. One moment, you're driving on a wet surface with adequate traction. The next, you're skating on a sheet of pure ice with virtually no control. This phenomenon is what makes highway pileups so common during these events. The drivers at the front of the squall hit the flash freeze first, losing control before the drivers behind them can even see the danger through the wall of snow. What makes this ambush so effective is the element of deception. Many snow squalls form on days that are otherwise clear, cold, and even sunny. You might be enjoying a beautiful winter afternoon with blue skies overhead when you notice something ominous on the horizon. It often looks like a dark, turbulent, and strangely low-hanging wall of cloud, churning and advancing with unnatural speed. It's a stark, terrifying contrast to the peaceful sky above. This visual is the squall line unmasking itself. Unlike a widespread blizzard that is preceded by hours of gray, overcast skies and gradually worsening conditions, a squall gives very little warning. It literally looks like a piece of a violent storm has broken off and is racing across the land, ready to engulf everything in its path. It's this profound and rapid shift from tranquility to turmoil that catches so many people completely unprepared, turning a routine drive into a fight for survival. What's the most sudden weather change you've ever witnessed? Describe it in the comments below. It's fascinating to see how winter surprises hit different parts of the world. This intense, localized nature is precisely what separates a snow squall from its more famous cousin, the blizzard. It's a common misconception to use the terms interchangeably, but in the world of meteorology, they are worlds apart. Think of it this way. A blizzard is a long, grueling siege, while a snow squall is a lightning-fast raid. A blizzard is a large-scale storm system, often spanning hundreds of miles, and is defined by strict criteria. Sustained winds of at least 35 miles per hour and visibility reduced to less than a quarter mile, all lasting for a prolonged period, typically 3 hours or more. It's about endurance. A snow squall, on the other hand, is all about intensity over a short duration. Its winds can be even stronger than a blizzard's, but the entire event might pass over a single location in just 30 to 60 minutes. It's a creature of hit-and-run tactics, defined not by its longevity, but by the sheer shock of its arrival and the severity of its brief passage. So, if it's not part of a massive, lumbering storm system, what kind of atmospheric recipe cooks up such a localized monster? The answer lies in a phenomenon called atmospheric instability, often triggered in one of two ways. The most well-known is the lake effect or ocean effect snow squall. This happens when a very cold, dry air mass, typically from the Arctic, flows over a relatively warmer body of water. The water, which retains heat longer than land, warms the air at the very bottom of the air mass. This warmer, moisture-rich air is now less dense than the frigid air above it, so it begins to rise rapidly, creating powerful updrafts. As it rises into the colder atmosphere, that moisture condenses and freezes into snow crystals, forming narrow, intense bands of snow that are then deposited on the downwind shore. The second type is the frontal squall, which occurs along a sharp, cold front. The dense, cold air acts like a wedge, aggressively forcing warmer, moist air upwards, creating the same kind of violent lift and resulting in a narrow, fast-moving line of intense snow. This formation process is also what gives the squall its terrifying speed. These are not stationary weather events, they are on the move and fast. A typical snow squall line travels across the landscape at speeds of 30 miles per hour or about 50 kilometers per hour, and sometimes even faster. To put that in perspective, it can cross the length of a football field in about 7 seconds. For drivers on a highway, this is a critical and often underestimated fact. A squall appearing on the horizon a few miles away is not a distant threat. It can be on top of you in the time it takes to listen to a single song. This forward momentum is why you can enter a squall on a perfectly clear road and, less than a minute later, be plunged into a complete whiteout with icy conditions, while the stretch of road you were just on remains sunny and dry. Ultimately, the speed and the snow converge to create the squall's signature attack, the whiteout. This isn't just a poetic term for heavy snow, it's a specific and deeply disorienting phenomenon. A true whiteout occurs when the density of falling and blowing snow becomes so great that it diffuses the sunlight completely. The sky and the ground blend into a single, seamless expanse of white, with no shadows, no horizon, and no visible features to give you a sense of depth or orientation. Your brain is starved of the visual cues it needs to perceive distance and direction. This can induce a powerful sense of vertigo even if you're standing still. For a driver, it is catastrophic. The road, other cars, and even the front of your own vehicle can seem to disappear into an endless, featureless void. It's this complete sensory deprivation, combined with the sudden ice and violent wind, that truly defines the terror of being caught in winter's ultimate ambush. It strips away your most critical sense, leaving you blind and vulnerable at the worst possible moment. So, we've seen the atmospheric ingredients that cook up a snow squall. But knowing the recipe is one thing. Witnessing the meal get served is something else entirely. It's a storm defined not by how much snow it drops, but by how fast it changes your world. And that speed is the first thing that catches people off guard. When a snow squall gets organized and starts moving, it doesn't drift, it sprints. These narrow bands of intense weather can travel across the landscape at speeds of 30 miles per hour or even faster. To put that in perspective, that's the speed of a charging grizzly bear or a car driving down a residential street. You can literally watch it race towards you, swallowing up the horizon in a matter of minutes. This isn't your lazy, picturesque snowfall. This is an atmospheric ambush, and its incredible forward momentum is why you can go from a perfectly clear day to a total blizzard in the time it takes to find your winter gloves. And as this high-speed storm barrels towards you, the first thing you see is often the most terrifying. Observers on the ground don't just see snow approaching, they see what looks like a solid object, an advancing wall of white. This isn't just an illusion.
The leading edge of a snow squall is so abrupt, and the snowfall within it is so concentrated that it creates a visually distinct vertical wall of snow and wind. Visibility can drop from several miles to less than a quarter mile, often down to complete zero in under a minute. One moment you're driving under blue skies, the next you're inside a churning, opaque cloud that has descended to the ground. This sudden, disorienting loss of all visual reference is what makes squalls so uniquely dangerous, especially on highways. The world simply vanishes behind a curtain of white that you didn't see coming until it was already on top of you. But behind that blinding wall of white is an invisible enemy that hits you just as hard: a shocking drop in temperature. A snow squall is, at its heart, a blast of Arctic air. As the squall line passes over, it brings a dramatic and almost instantaneous temperature plunge. We're not talking about a gradual cooling over an hour. It's common for the temperature to fall 10 to 20 degrees Fahrenheit. That's about 5 to 11 degrees Celsius in just a few minutes. This sudden thermal shock is caused by the gust front, the leading edge of the cold air mass, forcing the warmer, moister air ahead of it violently upward. This process both fuels the storm's intensity and replaces the mild air with a frigid blast, catching anyone outdoors completely unprepared for the sudden, biting cold that arrives with the snow. This frigid blast of air doesn't arrive gently. It's pushed by a force that can literally spin you around. The passage of a squall line is almost always marked by a powerful and abrupt wind shift. The winds ahead of the squall might be relatively calm or coming from one direction, but as the front hits, the wind speed can instantly double or triple, with gusts exceeding 50 miles per hour, all while shifting direction dramatically. This happens because the squall acts like a miniature cold front with its own circulation and pressure differences. This sudden, violent change in wind direction and speed is not only disorienting, but can create chaotic, swirling snow that reduces visibility even further and makes simple things like walking in a straight line nearly impossible. Have you ever been caught in a wind that seemed to change directions on a dime? Share that wild experience in the comments below. And in the most turbulent of these squalls, that chaotic wind and unstable air can cook up something truly bizarre, a weather phenomenon that many people don't even believe is real: thunder snow. Yes, you heard that right, thunder and lightning inside a snowstorm. While incredibly rare, it can happen when there's an unusual amount of atmospheric instability and lift within the squall. The same violent updrafts that create the heavy snow can also cause enough separation of electrical charge within the cloud to produce a lightning strike. The thunder that follows is often described as a low, deep rumbling, muffled by the sound-absorbing quality of the falling snow. It's an eerie, awe-inspiring event that proves just how much raw power is churning inside these compact, ferocious storms. Seeing a flash of lightning illuminate a whiteout is an experience you would never forget. A storm with the power to generate its own thunder and lightning sounds like it would last for days, right? Well, here's where snow squalls get truly strange. Despite their apocalyptic arrival and ferocious intensity, they are incredibly brief. The very definition of a squall is its transient nature. Most snow squalls pass over a given location in under an hour, with the most intense period of heavy snow and high winds often lasting for only 15 to 30 minutes. This is a stark contrast to a blizzard, which is a long-duration event that can last for many hours or even days. A snow squall is a meteorological hit-and-run. It unleashes all its fury in one concentrated, short-lived burst and then moves on, often leaving clear, sunny skies in its wake as quickly as it arrived. This shocking brevity is one of the squall's most defining and, frankly, weirdest characteristics. But don't let that short lifespan fool you. The most insidious danger a snow squall leaves behind can linger long after the last snowflake has fallen. It's a threat called the flash freeze. Here's how it works. Just before the squall hits, temperatures are often just above freezing, meaning surfaces like roads and sidewalks might be wet from rain or slightly melted snow. Then the squall passes through, dropping the temperature by 20 degrees in minutes. This sudden plunge into deep freeze territory instantly turns all that liquid water into a treacherous, invisible layer of ice. Pavement that was merely wet one minute becomes a skating rink the next. This rapid transition from wet to ice, happening just as the sun might be coming back out, creates some of the most hazardous road conditions imaginable, a hidden threat that catches countless people by surprise. It's not the amount of snow that makes them so terrifying, it's the timing. The sheer, shocking speed with which they can steal a perfectly clear day and twist it into a life or death scenario is what truly defines their power. We've talked about what a snow squall is, but now we need to understand its most dangerous weapon, surprise. Because a key feature that separates a snow squall from a simple snow shower is its connection to a dramatic, rapid temperature drop. This isn't a gentle slide into colder weather. The leading edge of a squall is an Arctic front in miniature, a bulldozer of frigid air. As it slams into a region, temperatures can plummet by more than 10 degrees Celsius or 20 degrees Fahrenheit in just a few minutes. This shocking drop creates an immediate and treacherous hazard known as a flash freeze. Any moisture on the roadways, be it from melting snow, recent rain, or even just residual dampness, doesn't have time to evaporate. It instantly crystallizes into a sheet of transparent, nearly invisible black ice. A road that was perfectly safe and merely wet one moment becomes a frictionless skating rink the next, and this often happens just as the heavy snow begins to fall, catching drivers completely off guard. And that brings us to the most disorienting aspect of a squall's arrival, the instantaneous loss of visibility. This isn't a gradual thickening of the air. It is an abrupt, cinematic plunge into a whiteout. 1 second, you can see for miles down the highway. The next, you can barely make out the hood of your own car. Visibility can drop from over 10 kilometers to less than 400 meters, what's considered near zero visibility in the span of a single minute. This sudden sensory deprivation is the primary cause of the catastrophic multi-vehicle pileups associated with these events. The human brain simply can't process the change fast enough. Your perception of speed becomes warped, your sense of distance vanishes, and the car that was a safe distance ahead of you moments ago is now an imminent, stationary threat hidden behind a curtain of white. For those who see one coming, the experience is unforgettable. A snow squall often doesn't roll in like a typical storm front, with darkening clouds that gradually cover the sky. Instead, it can appear on the horizon as a distinct, churning, and often turbulent wall of white. This formation looks exactly as it sounds, a literal, advancing wall of snow and wind moving across the landscape. It's a stark and menacing visual, with a clear line separating the blue sky and sunshine from the impending chaos. This wall can move astonishingly fast, sometimes at speeds exceeding 50 kilometers or 30 miles per hour. Watching this wall of snow devour the landscape as it races toward you is a profoundly unsettling experience, as it provides a visual countdown of the mere seconds you have before conditions deteriorate completely. Here's where it gets truly bizarre, though. The phenomenon of a sun squall is a perfect example of this storm's deceptive nature. Because of the squall's narrow, linear structure, it's entirely possible for the event to strike while the sun is still shining brightly. Imagine driving under a clear, blue sky with brilliant sunshine warming your car, only to be suddenly engulfed by a blinding blizzard. The sun might still be visible in your rearview mirror or off to the side, creating a surreal and confusing environment where intense light mixes with impenetrable snow.
This paradox messes with a driver's instincts, which equate sunshine with safety. What's the most visually strange weather phenomenon you've ever personally witnessed? Let me know down in the comments. These stories are always fascinating. Part of the reason these squalls are so successful in their ambush is because they can be masters of disguise, even to meteorologists. On weather radar, a classic large-scale winter storm system is easy to spot. It's a massive, sprawling blob of precipitation. A snow squall, however, often appears as a thin, narrow line or a series of smaller, broken-up cells. It might not look particularly threatening on a radar scan, especially to the untrained eye. Its intensity is often underestimated until it's directly over a populated area. Advanced Doppler radar can detect the strong winds associated with the front, but the squall's small scale and rapid evolution mean that by the time it's clearly identified as a major threat, it may already be impacting people on the ground. This leads to a critical psychological trap, the illusion of duration. While a blizzard can last for days, a snow squall is brutally intense but mercifully brief. The entire event, from the first flake to the last, might only last 30 to 60 minutes. The period of heaviest snow and strongest winds is even shorter, often just 5 to 15 minutes of pure chaos. This short lifespan creates a dangerous mindset. A driver caught in the initial moments might think, "It's just a quick flurry, I can push through it." They fail to realize that the most perilous part of the entire event is its first few minutes, the very window of time they're trying to drive through. By the time the squall passes and the sun reemerges, the damage, the multi-car pileup, has already been done. Ultimately, this incredible burst of energy is all thanks to a sudden atmospheric release. The chaos begins when a cold front, a leading edge of dense, cold air, wedges itself underneath warmer, less dense air. But in the case of a squall, this interaction is particularly abrupt. The atmosphere doesn't have time to adjust gradually. Instead, a sharp drop in barometric pressure occurs right along the frontal boundary, acting like pulling a trigger. This pressure plunge forces the warmer air to rise violently and rapidly. As it shoots upward, all the moisture it holds cools and condenses instantly, creating a torrent of snowflakes. It's not a slow brewing of a storm. It's a meteorological detonation, unleashing all its energy in one concentrated, fast-moving line. This is why it's not a storm that builds, but a storm that simply arrives. It is this explosive birth that makes the transition from clear to chaos a matter of mere seconds. Imagine driving on a perfectly clear winter day. The sun is out, the sky is a brilliant blue, and the road ahead is dry. Suddenly, you see a menacing, dark cloud on the horizon. Within minutes, that cloud is on top of you, and the world outside your car vanishes into an instantaneous, violent whiteout. This isn't just a storm. It's a snow squall, a true micro-blizzard with a very specific and surprisingly complex anatomy. And today, we're going to dissect one, piece by piece. If you're ready for more amazing weather facts, make sure you hit that like button and subscribe so you never miss an update. Let's start with the squall's most defining feature, its verticality. While a widespread snowstorm might come from vast, layered stratus clouds stretching for hundreds of miles, a snow squall is born from a single, towering cumuloform cloud, often a cumulonimbus or towering cumulus. This cloud isn't wide, it's tall. In fact, the tops of these snow squall clouds can rocket upwards to heights of 10,000 to 20,000 feet. That's like stacking more than a dozen Empire State Buildings on top of each other. This immense vertical structure is the first clue that you're dealing with something far more energetic and concentrated than a typical snow event. It's an atmospheric skyscraper built in minutes, designed for one purpose: to dump an incredible amount of energy and precipitation on a very small area. But what's powering this vertical monster? It's not just cold air. The engine of a snow squall is an intense cycle of updrafts and downdrafts moving at incredible speeds. Inside that towering cloud, powerful updrafts of warmer, moist air are shooting upwards at speeds that can exceed 30 miles per hour. This is the fuel, rapidly lifting moisture into the freezing upper levels of the atmosphere. Simultaneously, supercooled air and heavy precipitation create intense downdrafts that plummet back towards the Earth. This violent internal circulation is what makes a squall so ferocious. It's not a gentle release of snow. It's a turbulent, churning machine that literally wrings moisture out of the sky and blasts it downwards. This internal battle between rising and falling air is why the snowfall is so heavy and the winds are so strong. It's a perfectly contained, miniature atmospheric blender. Have you ever felt that sudden, violent wind just before a storm hits? Let me know in the comments what that experience was like. The first part of this machine to reach you on the ground is what meteorologists call the gust front. This is the leading edge of the squall, and it's a dramatic announcement of what's to come. Pushed out by the powerful downdrafts, this boundary of cold, dense air races ahead of the main snowfall. The gust front is responsible for the sudden, drastic change in conditions. One moment, the wind might be calm, and the next, you're hit with gusts of 40, 50, or even over 60 miles per hour. This isn't just wind, it's a wave of frigid air that can kick up existing snow from the ground, creating blizzard-like conditions even before the first new flake has fallen. This leading edge is often visible as a dark, turbulent, and rapidly advancing wall of cloud and snow, a true shelf cloud in winter. It's nature's final warning signal. Once that gust front passes, you enter the heart of the beast, the precipitation core. And this is where the squall earns its terrifying reputation. A snow squall's core is incredibly narrow, often just a few miles wide. But what it lacks in breadth, it more than makes up for in intensity. Snowfall rates inside this core can be astronomical, reaching 2, 3, or even 4 inches per hour. Think about that. In just 15 minutes, an entire inch of snow can blanket the ground, instantly turning a clear road into an impassable sheet of white. This intensity is what causes the infamous whiteout conditions, where visibility drops to near zero in seconds. The snow isn't just falling, it's being driven horizontally by the fierce winds, creating a disorienting, blinding vortex of white. You are literally inside the most intense part of the storm's engine. What's the most intense, short-burst snowfall you've ever been caught in? Share your story below. At the same time you're being hit by the wind and snow, another dramatic event is happening to the air itself. The powerful downdraft isn't just bringing down wind and snow, it's dragging down a massive pocket of intensely cold air from high up in the atmosphere. This results in a sudden and often shocking temperature drop on the ground. It's not uncommon for the temperature to plummet 10 to 20 degrees Fahrenheit in the span of just 5 to 10 minutes as the squall line passes over. This rapid thermal shock can turn wet roads into sheets of ice almost instantaneously, creating the infamous flash freeze that makes travel so treacherous. You can go from a slightly above freezing drizzle to a full-blown Arctic deep freeze in the time it takes to listen to a couple of songs. It's that thermal shock that's so disorienting. Drop a comment if you've ever experienced a temperature swing that fast. But here's one of the most bizarre parts of a snow squall's anatomy: its ending. After the terrifying chaos of the core, the storm's departure is just as abrupt and dramatic as its arrival. The back edge of a snow squall is incredibly well defined. Because the system is so narrow and moving so fast, you can go from a complete, blinding whiteout to bright sunshine and clear blue skies in less than a minute. One moment, you can't see the hood of your car. The next, you're squinting in the sun, watching the wall of snow recede in your rearview mirror. This sharp clearing line is a hallmark of a squall. It's not a gradual tapering off of snow. It's like a switch being flipped, leaving behind a fresh, deep blanket of snow under a pristine sky, as if the storm was never even there. That sudden return to sunshine is almost as jarring as the start. Have you seen a storm end that quickly? I'd be curious to read about it. Finally, let's zoom out and look at the squall's overall shape and scale. Unlike the vast circular low-pressure systems that cause multi-day blizzards, a snow squall almost always organizes itself into a long, narrow band. This line can be hundreds of miles long, but as we discussed, it may only be 5 to 20 miles wide. This linear shape is why a squall's impact is so localized, but also so dangerous along its path. A town 10 miles to the north or south of the squall line might see nothing but a few flurries and a bit of wind. But for everyone directly in its path, it's a full-blown, albeit short-lived, blizzard. This ribbon-like structure, often called a squall line, sweeps across the landscape like a broom, concentrating all its fury along that narrow, moving path, leaving a distinct trail of chaos and heavy snow in its wake. It's the definition of a high-impact, small-footprint weather event. Imagine you're driving down a highway on a cold but sunny winter day. The road is clear, the sky is blue. In the distance, you see a dark cloud, but it doesn't look like much. 60 seconds later, your world vanishes. You're plunged into a blinding, swirling chaos of white. You can't see the car in front of you. You can't see the lines on the road. This isn't just a snow flurry. It's a snow squall, and it's one of the most terrifying and lethal weather phenomena a driver can ever face. We've talked about the science behind snow, but now we're heading onto the asphalt to see what happens when this weather turns violent. The danger of a snow squall isn't the amount of snow it drops, but the shocking speed at which it arrives. In literally the time it takes to change a song on the radio, visibility can plummet from over 10 miles to less than a quarter of a mile, and often to complete zero. This sudden, disorienting blindness is the primary factor in the catastrophic pileups they cause. Drivers traveling at highway speeds are suddenly robbed of their most crucial sense, with no time to react or comprehend what's happening. One moment, they're cruising along. The next, they're inside a giant, swirling ping-pong ball with thousands of pounds of metal moving on all sides, completely unseen. What makes them so treacherous is that they often defy prediction, at least on a personal level. Your standard weather app might call for a chance of flurries, giving no hint of the impending danger. This is because snow squalls are mesoscale events, meaning they are smaller and more localized than the large-scale systems that produce blizzards. They often form along a sharp Arctic cold front, a boundary of colliding air masses. These fronts can be narrow, sometimes only a few miles wide, but stretch for hundreds of miles long. They move quickly, and the squall acts like a shock wave on the leading edge of this frigid air, slipping through the cracks of broader regional forecasts. To a driver, it truly feels like it appears out of a clear blue sky. The arrival of a squall isn't just a visual event, it's a full-blown thermal assault. As the front passes over, the air temperature can plummet with breathtaking speed. It's not uncommon for the temperature to drop 10, 15, or even 20 degrees Fahrenheit in a matter of 5 to 10 minutes. This isn't a gradual cooling, it's a sudden, jarring plunge into Arctic conditions. This rapid temperature drop is the engine of the squall, driven by the intense upward and downward motions of air within the front. It's a literal wall of cold air hitting warmer, moister air, and the result is an explosion of frozen precipitation. Have you ever been caught in a sudden, intense storm while driving? Tell us about your experience in the comments. Here's where it gets truly insidious, creating the invisible killer on the highway. Often, just ahead of the intense snow, the squall will produce a brief burst of rain or sleet. This initial precipitation wets the pavement, which might still be above freezing. But then, that 20-degree temperature drop hits. The super chilled air accompanying the heavy snow instantly freezes the wet road surface, creating a perfect, transparent sheet of black ice. Drivers who are already struggling with zero visibility are suddenly driving on a surface with virtually no friction. The road doesn't look icy, it just looks wet through the swirling snow. They hit the brakes, and absolutely nothing happens. This terrifying combination of sudden whiteout conditions and instantaneous black ice is a recipe for disaster, and snow squalls are notorious for causing some of the most massive chain reaction pileups ever recorded. We're not talking about a handful of cars. We're talking about incidents involving 50, 70, sometimes well over 100 vehicles. A squall moves across a busy interstate, and in minutes, a stretch of highway is transformed into a tangled scrapyard of crushed cars, jackknifed tractor trailers, and injured motorists. The speed of the event means that by the time the first collision happens, dozens of other drivers behind it are already too close and moving too fast to stop, plowing into the wreckage one after another in the blinding snow. What's the most extreme weather condition you've ever had to drive in? Share your story below. The danger is so distinct and so severe that meteorologists and public safety officials have had to completely rethink how they warn the public. For years, the language of snow showers or flurries failed to convey the life-threatening nature of these events. In response, the National Weather Service in the United States created a specific snow squall warning. This is a major development. These warnings are now issued with the same level of urgency as a tornado warning or a severe thunderstorm warning. They are geographically targeted and sent as wireless emergency alerts that will set off a loud alarm on your cell phone, telling you to take immediate action or avoid travel. This isn't a suggestion to be careful. It's an emergency alert telling you that a life-threatening event is imminent. Do you think these kinds of mobile alerts are effective, or do people just ignore them? Let me know your thoughts. So, what is that immediate action? What should you do if you're on the highway and find yourself engulfed by this invisible killer? The advice from safety experts is deeply counterintuitive but absolutely critical for survival. First, do not slam on your brakes. This will almost certainly cause you to lose control on the flash-frozen road. Instead, take your foot off the accelerator and slow down as gradually as possible. Turn on your hazard lights immediately. Increase your following distance to the absolute maximum you can. If you can see an exit, take it. But if you are trapped and forced to stop, the most vital and surprising piece of advice is this. Once you pull over as far as you can, turn your headlights and taillights off. This seems insane, but it prevents a deadly mistake. In a whiteout, a following driver can't judge distance. They will see your taillights, assume your vehicle is moving, and drive directly towards them, rear-ending you at high speed. By turning your lights off, once you are safely stopped off the roadway, you remove that fatal target. Turning off your lights in a storm sounds terrifying, but makes total sense when you think about it. What's the most counterintuitive safety tip you've ever learned? The highway snow squall remains one of nature's most perfectly designed traps. It's a combination of extreme elements unleashed with surgical precision and terrifying speed. It isn't the depth of the snow, but the depth of the surprise that makes it so deadly. It exploits the limits of our perception and the physics of our vehicles, turning a routine drive into a nightmare in less time than it takes to read a road sign. But these ferocious squalls don't just happen on land. The same atmospheric dynamics that cause chaos on our highways can create bizarre and beautiful phenomena over water, in places you would never expect. And that's exactly where we're headed next. And while we now understand the anatomy of a squall, a critical question still hangs in the icy air. Isn't that just a really fast snowstorm? The answer is a resounding no. And the difference isn't just a matter of semantics, It's the difference between inconvenience and immediate, life-threatening danger. The distinction between a snow squall and a winter storm is one of the most misunderstood concepts in meteorology, so let's clear the air, because knowing the difference could one day be critical. The most fundamental way to separate a squall from a storm is to look at your watch. A true winter storm, like a blizzard or a nor'easter, is a marathon event. It settles in for the long haul, battering a region for hours, sometimes even for days on end. It's an atmospheric siege. A snow squall, on the other hand, is a violent sprint. Its entire lifespan, from the first flake to the last, is often measured in minutes, not hours. A typical squall will assault an area with blinding intensity for maybe 15 to 30 minutes and rarely more than an hour. Then, just as abruptly as it began, it's gone. This extreme brevity is what makes them so treacherous. A large storm gives you time to prepare, to get home, to hunker down. A squall offers no such courtesy. It arrives with the suddenness of an ambush, demanding you react to a worst-case scenario in a matter of seconds. Now, let's zoom out and look at the battlefield from above. This is where the next crucial difference becomes visually obvious. A winter storm is a sprawling, monstrous entity on a weather map, often covering multiple states in a vast, swirling mass of precipitation. It's a blunt instrument, affecting millions of people over a huge geographical area. A snow squall is the opposite. It's a meteorological scalpel. It is almost always a linear feature, a narrow, intense band of snow that might only be a few miles wide, but can stretch for 100 miles or more in length. This is why you can be driving on a highway, see a terrifying wall of white in the distance, plunge into it for 5 minutes of pure chaos, and then emerge back into sunshine on the other side, while areas just a few miles north or south of you experience nothing but a light flurry. Its localized, ribbon-like nature is a defining characteristic that separates it entirely from the widespread, all-encompassing blanket of a major snowstorm. Think of the mechanics behind them. A large winter storm is typically born from a large-scale, low-pressure system, a cyclone. This system acts like a giant, slow-spinning engine, drawing in moisture over vast distances and methodically converting it into widespread, prolonged snowfall. It's a complex, lumbering process that meteorologists can often track for days as it develops and moves across the continent. A snow squall's engine is far more focused and explosive. It's most often created by the sharp, leading edge of an Arctic cold front. As this frigid, dense air plows into warmer, moister air, it forces that warm air to rise violently and rapidly, like a wedge being driven underneath it. This sudden, powerful upward motion creates a narrow band of extreme condensation and heavy snow right along the frontal boundary. It's not a slow spin, it's a violent, forward-punching shock wave in the atmosphere. Have you ever experienced one of these sudden, front-driven whiteouts? Tell us in the comments what that shocking transition felt like. This difference in formation leads directly to a difference in their primary threat. While both events are dangerous, they try to get you in different ways. A blizzard's main weapon is accumulation and endurance. It seeks to bury you. The sheer volume of snow, combined with sustained high winds, creates massive drifts, closes roads for days, and can lead to structural collapse and power outages. Its danger lies in its overwhelming, relentless presence. A snow squall's primary weapon is the instantaneous and total loss of visibility. The snowfall rate can be so extreme, 2, 3, even 4 inches per hour, that it creates a complete and sudden whiteout. One moment you can see a quarter mile down the road, the next you can't see the hood of your own car. This rapid degradation of sight is the #1 cause of the catastrophic multi-vehicle pileups associated with squalls. The snow accumulation is secondary. The true danger is the blinding curtain that drops with no warning. Because their threats are so different, our systems for warning the public have had to evolve. A winter storm warning is a large-scale, long-duration alert. Meteorologists issue these 12 to 24 hours, sometimes even 36 hours in advance. It tells the population of a broad area to prepare for a significant multi-hour weather event. It's a strategic warning. The snow squall warning, however, is a much newer and more tactical tool, first implemented nationwide in the US in late 2018. It functions more like a tornado or severe thunderstorm warning. It's issued for a very small, specific area, often targeting a corridor along a major highway, and for a very short period, typically 30 to 60 minutes. The alert is designed to be jarring, sent directly to smartphones with the urgent message: an imminent, life-threatening hazard is approaching your location. Take shelter or delay travel now. This targeted, high-urgency system reflects the squall's nature as a fast-moving, localized, but extreme threat. Perhaps one of the most dramatic distinctions is what happens to the thermometer. During a large winter storm, temperatures will fall, but it's usually a gradual process over many hours as the cold air associated with the system filters in. A snow squall, however, is famous for producing a phenomenon known as a flash freeze. Because the squall is riding the razor's edge of an Arctic front, the temperature drop is breathtakingly fast and severe. It's not uncommon for the temperature to plummet 20 degrees Fahrenheit, or around 11 degrees Celsius, in a matter of minutes. This means any wet or slushy surfaces, roads, bridges, overpasses, instantly turn into a sheet of black ice the moment the squall line passes. This happens simultaneously with the blinding snow, creating a 1-2 punch of zero visibility and zero traction, an absolutely lethal combination for anyone on the road. Finally, consider the aftermath. After a major blizzard, the sky might clear, but the world is fundamentally changed for a day or two. You are left to dig out from under a heavy blanket of snow, a clear and lasting reminder of the storm's power. The aftermath of a snow squall is almost surreal and deceptive. Because the event is so brief and the accumulations are often minor, perhaps just an inch or two, the sun can reappear moments after the squall passes. The sky turns blue, the world looks bright and clean, and it can be difficult to believe that the terrifying whiteout you just survived even happened. This deceptive clearance is a signature of the squall, a rapid return to normalcy that belies the chaos it unleashed just minutes earlier, leaving behind a legacy not of deep snow, but of sudden, tragic consequences. Understanding these core differences is the first step in truly respecting the unique and formidable power held within that narrow, fleeting line of white. The sun is out, clear, cold winter day. The sun is out, glinting off the frozen landscape, and the road ahead is perfectly visible for miles. Then you see it on the horizon, a dark, turbulent wall of cloud advancing with unnatural speed. Within 10 minutes, the sun is gone. Within 5, the world outside your windshield dissolves into a chaotic, blinding vortex of white. Visibility drops from miles to mere feet. This isn't a typical snowstorm. This is an atmospheric ambush. And the science behind its sudden, violent strike is one of meteorology's most fascinating and dangerous phenomena. To understand how a snow squall can materialize seemingly out of nowhere, you first have to grasp a fundamental concept: atmospheric instability. On a day ripe for a squall, the air isn't a uniform blanket. It's secretly layered in a highly volatile arrangement. Close to the ground, there's a pocket of relatively mild, moist air. But just above it, a mass of much colder, denser, and drier air is sliding into place. This setup is incredibly unstable, like a layer of water trapped beneath a layer of oil. The cold, heavy air wants to sink, and the warmer, lighter air wants to rise. It's a coiled spring of atmospheric energy, waiting for the slightest trigger to release its power in a violent upward explosion. This hidden tension is the secret fuel that allows a squall to erupt with such shocking speed, turning a calm day into chaos without the long, gradual buildup of a traditional winter storm. That trigger is almost always the arrival of a sharp, powerful Arctic cold front. But thinking of this front as just cold air is a massive understatement. In the context of a snow squall, the leading edge of this cold air mass acts like a meteorological bulldozer. It's incredibly dense, and it moves fast, carving a path through the atmosphere. As this wedge of frigid air plows into the warmer, moisture-laden air near the surface, it doesn't just mix, it violently forces that lighter air upwards. This process is known as frontal lifting, and in the case of a squall line, it's brutally efficient. The ascent is so abrupt and focused along this narrow boundary that it creates a towering, narrow wall of cloud, the squall line itself. The sheer force of this lift is the engine that drives the entire event, and it's why the storm has such a distinct, menacing appearance as it approaches. This violent upward thrust of air is what we call convection. While we often associate convection with summertime thunderstorms, it's the same vertical engine that powers a snow squall, just in a frigid environment. The air is shoved upwards so rapidly that it can create vertical wind speeds of over 30 miles per hour within the cloud. Think about that for a second. Air rising faster than a person can sprint. This creates extreme turbulence and is the reason squalls are so structurally different from gentle snowfalls. Instead of clouds gradually thickening and lowering over hours, a squall cloud can shoot upwards to heights of 10,000 feet or more in under an hour. This vertical superhighway is what transports moisture from the surface to the freezing upper levels of the atmosphere at an incredible rate, setting the stage for the deluge to come. Have you ever been caught in a weather event that seemed to appear from absolutely nowhere? Share that story in the comments below. It's amazing how fast nature can move. But where does all that snow come from, especially when the day might have seemed quite dry? The answer lies in invisible water vapor. Cold air can't hold as much moisture as warm air, but the layer of air near the ground ahead of the squall is often surprisingly humid. As the cold front forces this air skyward, it undergoes a process called adiabatic cooling. As the air parcel rises, the pressure around it decreases, allowing it to expand. This expansion uses energy, which causes the air to cool down dramatically, often at a rate of about 5.4 degrees Fahrenheit for every 1,000 feet it ascends. This rapid chilling forces the invisible water vapor to instantly condense into tiny water droplets or ice crystals, forming the cloud. Because the lift is so strong, it wrings out nearly every last drop of moisture from the air in a very short amount of time, essentially squeezing the atmosphere like a sponge and dumping all its contents in one concentrated burst. Now, not all snowflakes are created equal, and the type of snowflake a storm produces is critical to how much it impacts visibility. Snow squalls are master craftsmen of a specific type of snowflake that is perfectly designed to create whiteout conditions. Inside that turbulent squall cloud, there is a sweet spot of temperature, typically between -12 and -18 degrees Celsius, known as the dendritic growth zone. In this zone, ice crystals grow into their most intricate and beautiful forms, the classic six-branched dendrites. These snowflakes have a huge surface area for their weight, like tiny parachutes. When they fall, they don't fall straight down. They flutter and float, staying airborne for longer and filling the air completely. The extreme vertical motion inside the squall cloud can even carry these snowflakes up and down multiple times, allowing them to grow even larger and more complex. It's this mass production of large, feathery dendrites that is the primary reason a snow squall can reduce visibility to absolute zero. What makes this process even more intense is that squalls can be supercharged by their environment, particularly large bodies of water. This is the science behind the infamous lake effect snow squall. When a frigid Arctic air mass, the primary driver of the squall, passes over a relatively warm, unfrozen lake, it's like throwing gasoline on a fire. The lake's surface, which might be many degrees warmer than the air above it, transfers a massive amount of heat and moisture into the bottom layer of the atmosphere. This adds extra buoyancy and an enormous amount of raw material for snowflake production. The air becomes even more unstable, the upward motion becomes more violent, and the snowfall rates become astronomical. A squall that might have produced a quick coating of snow over land can become a crippling, high-impact event after it crosses a large lake, capable of dumping several inches of snow in less than an hour. Perhaps the most unsettling scientific aspect of a snow squall, and the reason they are such a notorious forecasting challenge, is their independence. Unlike a massive blizzard, which is a key feature of a large, well-defined, and slow-moving low-pressure system that meteorologists can track for days, a snow squall is often a meteorological lone wolf. It's a mesoscale event, meaning it's smaller and more localized. Many squalls form along a cold front without any parent low-pressure cyclone nearby. This makes them incredibly difficult to predict with precision. Weather models, which are excellent at forecasting large-scale systems, can struggle to resolve these narrow, fast-moving bands of intense snow. They can see the potential is there, but pinpointing exactly where and when a squall will hit remains one of the toughest jobs in weather forecasting, leaving us to rely on short-term warnings for these sudden atmospheric assaults. Forecasting the weather is one thing, but predicting a snow squall is like trying to guess exactly where a single lightning bolt will strike in a thunderstorm. While meteorologists have an arsenal of incredible tools, the squall remains one of nature's most elusive and difficult to pinpoint threats. This isn't your typical day-ahead forecast. It's a high-stakes game of minutes and miles, and it's a field known as nowcasting. Unlike a massive blizzard system that can be tracked for days as it moves across the continent, a snow squall is a creature of the immediate present. Nowcasting focuses on the weather from 0 to 6 hours out, using a constant stream of real-time data to anticipate these rapid-fire events. Forecasters aren't looking at a weather map from yesterday to predict tomorrow. They're watching a live feed of the atmosphere, trying to spot the telltale signs of a squall forming right now, and issuing warnings sometimes only 15 to 30 minutes before it hits. It's a discipline that demands lightning-fast analysis because the entire life cycle of a snow squall, from birth to dissipation, can be shorter than your average movie. The absolute hero in this real-time battle is Doppler radar. You've probably seen the colorful maps on the news, but its power goes far beyond just showing where it's raining or snowing. The secret is in the name, Doppler. This technology doesn't just see precipitation, it sees movement. The radar sends out a beam of energy, and when that beam hits snowflakes or raindrops, it bounces back. If the snowflakes are moving toward the radar, the returning frequency is higher. If they're moving away, it's lower. This is the Doppler effect, and it allows meteorologists to create a detailed map of wind patterns inside the storm. For a snow squall, this is the holy grail of data. They can see the powerful gust front, the surge of wind that races ahead of the snow, and they can spot the intense rotational movements within the storm cell that signal its severity. It's the difference between knowing a car is on the road and knowing it's coming at you at 100 miles per hour. This velocity data is what allows forecasters to issue warnings that specifically mention life-threatening, whiteout conditions and extreme winds, a critical distinction from a simple snow shower. But the view from the ground only tells half the story. To get the full picture, forecasters look down from space. Modern weather satellites provide a bird's-eye view that can reveal the structure and character of the storm system in ways radar cannot.
While a squall itself might be small, it's often born from a much larger feature, like a powerful cold front.
On satellite imagery, these fronts can appear as a stunningly sharp, well-defined line of clouds marching across the landscape. Meteorologists look for specific visual cues that scream trouble. Is the leading edge of the cloud line particularly bright white and crisp? That indicates strong upward motion, a key ingredient for intense precipitation.
Sometimes they can even spot what are known as rope clouds, narrow, rope-like cloud lines that mark the boundary of the cold air surge. Seeing one of these on satellite imagery is a massive red flag that the conditions are ripe for squalls to fire up along that line, giving forecasters a precious lead time to alert the regions in its path. This incredible stream of data from radar and satellites is utterly useless without something to make sense of it all. This is where supercomputers come in, running what are known as high-resolution rapid refresh models, or HRR. Think of the HRR as the world's most sophisticated and impatient weather forecaster.
While standard forecast models might update every 6 or 12 hours and predict the weather for the next week, the HRR model updates every single hour and focuses only on the next 18 hours.
It ingests a colossal amount of real-time information, radar data, satellite images, weather balloon observations, and even data from commercial aircraft, and uses it to create an intensely detailed 3-kilometer resolution grid of the atmosphere. This allows it to see and predict small-scale phenomena like thunderstorms and, yes, snow squalls that older, broader models would completely miss.
Even with all this power, the HRRR can still struggle with the exact timing and location. It might show a high probability of a squall in a certain county, but pinpointing which specific highway will be impacted at what exact minute remains the ultimate challenge. Have you ever been completely blindsided by a storm that your weather app didn't even hint at?
Share your story in the comments below. It's amazing how often it happens. This is precisely why, even in an age of supercomputers and AI, the human element in forecasting is more critical than ever. The data from the models is a guidance, not a certainty. An experienced meteorologist acts as the final, crucial filter. They don't just look at the raw output, they interpret it.
They recognize patterns that the computer might not weigh as heavily, drawing on their knowledge of local topography, how hills, valleys, and bodies of water can dramatically influence a storm's behavior. A forecaster who has worked in a region for years develops a kind of gut feeling for how squalls behave there. They might see a setup on the models that looks borderline, but based on a similar event 5 years prior, they know it has the potential to become dangerous. They are the ones who make the final, difficult decision to issue a snow squall warning, a call that balances the need to alert the public against the risk of overwarning. It's a high-pressure judgment call that blends cutting-edge science with hard-won experience. And that human expertise is exactly what separates a professional forecast from the app on your phone. Most standard weather apps are designed for convenience and a broad overview, not for high-impact, short-fuse events like snow squalls. They typically pull their data from global, lower-resolution models that are fantastic for predicting if it will be sunny or cloudy 3 days from now, but they lack the fine detailed precision to resolve something as small and fast-moving as a squall line. The app might just show 40% chance of snow, lulling you into a false sense of security. It completely misses the nuance that the snow will be a 20-minute-long, zero-visibility blizzard with 50-mile-per-hour winds. This is why relying solely on a basic app for winter travel can be so dangerous, and why official warnings from national weather services, which are issued by human forecasters using all the high-resolution tools we've discussed, are infinitely more reliable when squalls are in the forecast. So what does the future hold for predicting these unpredictable plunges? The next great leap is already underway, and it's powered by artificial intelligence. Researchers are now training machine learning algorithms on vast archives of meteorological data, containing decades of radar scans, satellite images, and model outputs from thousands of past snow squall events. The goal is to teach the AI to recognize incredibly subtle and complex patterns that precede squall formation, patterns that even a human expert or a traditional physics-based model might miss. By analyzing the precise atmospheric ingredients and evolutions that led to squalls in the past, the AI can learn to spot those same fingerprints developing in real time with greater speed and accuracy than ever before. This could lead to warnings that are not only more precise in location and timing, but are also issued with even greater lead time, turning a 15-minute warning into a 30 or even 45-minute heads-up, a critical window that could make all the difference on a busy highway. Imagine a wall of white, a churning curtain of snow and wind moving across the landscape faster than you can run. It devours a sunny afternoon in seconds, plunging visibility to zero and temperatures into a free fall. This isn't a special effect from a blockbuster film. For millions of people, it's a very real phenomenon, a meteorological ambush that defines their winters. Welcome to the global hotspots of snow squalls. While these whiteout events can theoretically happen anywhere the conditions are right, there are specific places on Earth that have truly mastered the art of the squall. Our first stop is arguably the most famous snow squall factory on the planet, the Great Lakes region of North America. This area isn't just a hotspot, it's a super producer, thanks to a perfect, powerful recipe. When frigid, dry air from the Canadian Arctic sweeps down in late autumn and winter, it encounters the Great Lakes, which are still relatively warm and unfrozen. The temperature difference can be staggering, sometimes over 40 degrees Fahrenheit. This contrast acts like a giant engine. The cold air passing over the warm water sucks up immense amounts of moisture and heat, becoming unstable. This moisture-laden air then rises, cools, and condenses into clouds that organize into long, narrow bands ready to unleash their fury on the downwind shores. This brings us to a critical concept known as fetch. Fetch is the distance the wind travels over open water. In the Great Lakes, a longer fetch means the air has more time to gather moisture and energy, resulting in a more ferocious squall. For example, a wind blowing west to east across the entire length of Lake Erie will produce a much more intense snow squall for Buffalo, New York, than a wind blowing north to south across its shorter width. This is why certain areas, like the Tug Hill Plateau in New York or parts of Ontario, are notorious snowbelts. They are geographically positioned to receive the full, concentrated power of these lake-effect squalls, sometimes getting buried under several feet of snow, while towns just a few miles away see only sunshine. Now, let's jump across the globe to another world-class snow squall hotspot, the western coast of Japan. Here, the phenomenon is so profound it has shaped culture and created some of the snowiest inhabited places on Earth. The mechanism is remarkably similar to the Great Lakes, but on a grander scale. The culprit is the Siberian High, a massive, bitterly cold air mass that dominates Asia's winter. As this frigid, dry air pours out from Siberia, it travels across the relatively warm Sea of Japan. The sea infuses the air with a tremendous amount of moisture. This air then slams into the Japanese Alps that run down the spine of the country's main island, Honshu. The mountains force the air upward, a process called orographic lift, squeezing out every last drop of moisture as incredible amounts of snow. Areas like Sukayu Onsen can receive an average of 58 feet of snow per year, a testament to the sheer power of the Sea of Japan effect. This powerful role of mountains in generating squalls isn't unique to Japan. Mountain ranges all over the world act as squall triggers. When a mass of cold, unstable air approaches a mountain, it has nowhere to go but up. This rapid vertical movement is the perfect catalyst for a squall. The air cools as it rises, its moisture condenses violently, and a sudden, intense burst of snow is unleashed on the windward side of the mountain. The Rocky Mountains in North America and the European Alps are prime examples of this. Skiers and mountaineers know this phenomenon all too well. A beautiful, clear day in the mountains can transform into a disorienting, dangerous whiteout in a matter of minutes as a squall forms and races down a valley. Have you ever been caught in a sudden mountain squall? Share your story in the comments below. It's a humbling experience to witness a mountain create its own blizzard out of thin air. But you don't always need massive lakes or towering mountains. Some of the most rugged and unpredictable squalls occur along the world's northern coastlines, born from the cold fury of the North Atlantic. Places like Newfoundland in Canada, the Faroe Islands, coastal Norway, and even the northern coasts of Scotland are hotspots for what are known as polar maritime air mass squalls. The process begins with extremely cold air pouring off the Greenland ice sheet or Arctic sea ice. As this air travels south over the much warmer waters of the North Atlantic Ocean, it rapidly destabilizes. The ocean pumps heat and moisture into the base of the air mass, creating the buoyancy needed for powerful convective clouds. These squalls arrive with little warning, bringing fierce winds, heavy snow or hail, and dramatic drops in temperature to coastal communities accustomed to weather that can change at a moment's notice. Thinking of intense snow might conjure images of the northern hemisphere, but the planet's southern half has its own squall hotspots, though they are less populated. The Andes Mountains, particularly in the Patagonian region of Chile and Argentina, are a prime location. Here, cold, moisture-laden air moves in from the Pacific Ocean and is forced violently upward by the sheer wall of the Andes. This creates intense, localized snow squalls that contribute to the region's glaciers and ice fields. While the populations are sparse, these squalls are a critical part of the local climate, delivering the snowfall that sustains the region's water resources. It's a powerful reminder that the fundamental ingredients for a snow squall, cold air, moisture, and lift, can be found in surprising corners of the globe. What's fascinating is how these natural events interact with our man-made world, creating urban snow squall corridors. A squall moving into a major city like Chicago, Toronto, or Buffalo doesn't just pass over it, it interacts with it. The urban heat island effect, where cities are warmer than surrounding rural areas, can sometimes alter a squall's path, weakening it in some places or even slightly intensifying it in others. More dramatically, the urban canyon effect, created by skyscrapers, can channel the wind and snow. A squall's already powerful winds can be funneled and accelerated between tall buildings, creating microclimates of extreme intensity at street level. One block might experience a moderate snowfall, while just a few blocks away, the wind-driven snow creates a complete whiteout, showcasing how our own structures can amplify nature's fury. If you live in a big city, have you noticed weather acting strangely between the skyscrapers? Let us know your city's weirdest weather quirk. Ultimately, all these global hotspots are connected by a single, overarching atmospheric driver, the polar vortex. This massive expanse of cold, low-pressure air that typically swirls over the poles is the ultimate source of the frigid air needed to kickstart a squall. When the polar vortex is strong and stable, this cold air stays locked up in the Arctic. But when it weakens or wobbles, it can send lobes of intensely cold air plunging southward into the mid-latitudes. This polar plunge is the trigger event. It's the moment that the frigid air spills over the Great Lakes, pours across the Sea of Japan, and collides with mountain ranges around the world, activating these hotspots and unleashing the sudden, violent beauty of the snow squall. Understanding this connection is key to understanding why some winters are relatively quiet and others seem to feature an endless barrage of these dramatic weather events. Imagine this. One moment, you're driving down a clear highway. The sun is out, the road is dry.
The next, a wall of white descends, not gradually, but instantly. Your world shrinks to just the few feet of pavement in front of your windshield. This isn't a blizzard you saw coming for days. It's a snow squall, and you're now inside the whiteout zone. We've explored the raw physics and terrifying speed of these weather assassins, but the real question is, when that wall of white swallows you whole, what do you do? Because the choices you make in the next few seconds are, quite literally, the difference between life and death. The single most counterintuitive and life-saving action you can take when a snow squall hits is to do almost nothing. Your instinct screams to keep going, to push through it, to escape. But safety experts and state troopers have a unified, urgent message. See the squall, pull over immediately. The goal is to get as far off the road as possible, turn on your hazard lights, and take your foot completely off the brake. Why off the brake? Because in a whiteout, following drivers experience a terrifying phenomenon called target fixation. Your bright red brake lights become the only visible thing in the void, and their panicked brain will instinctively steer directly towards them, turning your car into a target for a multi-car pileup. By pulling over and turning off all lights except your hazards, you effectively become invisible and stationary, letting the chain reaction chaos unfold on the roadway you just vacated. It's a terrifying leap of faith, trusting that getting out of the flow of traffic is safer than being in it, but the statistics on squall-related pileups are chillingly clear. Now, let's say you can't pull over. The squall hits with such ferocity that you're trapped in your lane. The next critical survival fact involves a concept most drivers have heard of, but few truly understand in this context: overdriving your headlights. At night, this means driving so fast you can't stop within the illuminated distance your headlights provide. But in a snow squall, it's a different beast entirely. The intense, dense snowfall acts like a billion tiny mirrors, reflecting your headlight beams directly back at you. This creates a blinding wall of light, severely reducing your visibility instead of improving it. It's an optical illusion that tricks your brain into thinking you can see further than you actually can. The solution is to switch from your main beams to your fog lights, if you have them. Fog lights are mounted lower on the vehicle and cast a wider, flyer beam that cuts underneath the worst of the airborne snow, illuminating the road surface itself rather than the chaotic curtain of white falling in front of you. This small switch can be the difference between seeing a stopped car ahead and becoming part of it. This brings us to the crucial gear you need, because a snow squall survival kit is fundamentally different from a standard blizzard kit. A blizzard kit prepares you for being stranded for days: heavy blankets, lots of food, a shovel. A snow squall kit, however, is for immediate, high-intensity survival over a shorter period. The key isn't long-term warmth, it's short-term visibility and stability. This means your most important items are things you can deploy in seconds. Think high-visibility emergency markers or reflective triangles you can place behind your vehicle if you manage to pull over safely. It also includes things like a bag of cat litter or sand, not for warmth, but for traction. If you're stuck on a patch of instantaneous ice, pouring this under your drive wheels can provide just enough grip to get you to the shoulder of the road. It's about surviving the next 30 minutes, not the next 30 hours. Speaking of traction, here's a fact that might just save your life one day, using an item you definitely have in your car right now: your floor mats. In a true emergency, if your car is stuck on ice and you have no sand or kitty litter, you can take out your own floor mats, preferably the rugged rubberized ones, and wedge them under your spinning tires. The textured surface provides an emergency grip zone, a temporary patch of friction that can be just enough for the tire to bite into and propel the vehicle forward a few crucial feet. This can be the difference between getting stuck in a live lane of traffic and making it to the relative safety of the roadside. It's a brilliant piece of impromptu engineering born from desperation. What's the most clever, unexpected survival hack you've ever heard of using a common, everyday item? Let us know your stories in the comments. They could genuinely help someone. Once you are safely pulled over, another deadly misconception takes hold. Many people, worried about running out of fuel, will turn their car off completely to conserve gas. This can be a fatal error for two reasons.
First, and most insidiously, is carbon monoxide. As the snow falls with incredible speed, it can quickly block your vehicle's exhaust pipe. If your engine is running, the colorless, odorless gas has nowhere to go but back into the cabin of your car, incapacitating and killing the occupants without them ever realizing what's happening. The rule is to run the engine for only about 10 minutes every hour to keep the cabin warm, and before you do, you must get out and physically clear the snow away from your exhaust pipe every single time. It's a hassle, but it's absolutely non-negotiable for survival. The vehicle provides your only shelter from hypothermia, so you need the heat, but you have to manage it safely. On the road, our sense of safe distances evaporates in a squall. We're all taught the 3-second rule for following cars in good weather. In a squall, that rule is not just inadequate, it's a recipe for disaster. Visibility can drop from miles to near zero in the time it takes to blink. The road surface can flash freeze, turning asphalt into an ice rink instantly. In these conditions, your following distance needs to expand to 10 seconds or even more. This feels absurdly slow. It means picking a stationary object, watching the car in front of you pass it, and then counting a full 10 seconds before you pass it. This provides the buffer needed not just for your reaction time, but for the catastrophic loss of traction your tires will experience if you need to brake suddenly. In a squall, you aren't just driving, you're navigating a minefield where every other vehicle is a potential threat and space is your only armor. Finally, surviving a whiteout is as much a mental game as it is a physical one. And for this, we can actually look to the sky. Pilots who fly in clouds or heavy fog rely on something called instrument flight rules. They learn to ignore what their senses are telling them, the feeling of turning or dropping that might be a complete illusion, and to trust their instruments explicitly. Drivers in the snow squall can apply a similar principle. The disorienting, featureless white landscape can cause powerful vertigo. You can lose all sense of which way is up, whether you're veering off the road or if you're even moving at all. The key is to reduce your speed dramatically and focus on the few reliable indicators you have, the painted lines on the road immediately in front of you or the tracks of the car ahead. You have to consciously fight the sensory illusions. Resist the urge to make a sudden correction based on a feeling. Instead, make small, deliberate movements, trusting the tangible evidence of the road directly beneath you, just like a pilot trusting their altimeter in a cloud. Your brain will lie to you in a whiteout, the road won't. Mastering this mental discipline is the final and perhaps most difficult piece of the survival puzzle. You're driving down the highway on a cold but perfectly sunny afternoon. The sky is a brilliant, crisp blue. Then you see it on the horizon, a dark, menacing wall of white moving impossibly fast. In the time it takes to change the radio station, you're plunged from clear daylight into a blinding, swirling vortex of chaos. This isn't a blizzard, it's a snow squall, and the truth behind these weather assassins is far more surprising than you can imagine. We often think of snow squalls as just intense, short-lived snowstorms, but that's like calling a tiger a house cat. The real story is in the physics, the deception, and the sheer, raw power they hide. One of the most terrifying aspects is that they are masters of disguise. Unlike a massive blizzard that you can see developing for days, many of the most dangerous squalls are born from what looks like a perfectly fine day. They can rapidly intensify from a few harmless-looking cumulus clouds into a full-blown whiteout emergency, often forming under a sky that was clear and blue just an hour earlier. This blue sky origin is what makes them so good at catching drivers and even meteorologists completely off guard. But what gives them that sudden, violent punch? It's not just about what's happening horizontally, but vertically. Inside a potent snow squall, the air isn't just moving forward, it's being shot upwards at incredible speeds. These updrafts, the very engine of the storm, can scream skyward at over 30 miles per hour. This vertical wind is what lofts snowflakes, even small ones, and holds them in the air, creating the blinding, impenetrable wall of white that defines a squall. It's less like snow falling and more like a curtain of snow being violently shaken in front of your face. It's this intense vertical motion that can reduce visibility from miles to absolute zero in less than a minute. And this rapid assault on the senses is matched by an equally sudden attack on the environment itself, leading to one of its most insidious dangers, the flash freeze. Picture this. The sun has been out. The road is wet from some earlier melting, and the surface temperature is a few degrees above freezing. Then the squall hits. The temperature can plummet 10 to 20 degrees Fahrenheit in a matter of minutes. That wet, harmless-looking pavement instantly transforms into a treacherous sheet of black ice, hidden under the fresh, rapidly accumulating snow. This isn't a gradual freeze, it's an instantaneous trap, and it's the primary reason snow squalls are responsible for some of the most catastrophic multi-car pileups on winter highways. The conditions change faster than any driver can possibly react. Now, here's where it gets even stranger, moving beyond the visual and into the audible. A powerful snow squall can create a bizarre and deeply disorienting acoustic bubble. As the wall of snow hits, the sheer density of the billions of falling snowflakes acts as a powerful sound dampening material. It can absorb ambient noise, creating a sudden, eerie, and unnatural silence. Yet this quiet is immediately contrasted by the ferocious roar of the wind. This combination of profound silence and deafening wind creates a sensory paradox that can be completely unnerving. You're trapped in a world where you can hear the storm's rage, but nothing else. A truly isolating and frightening experience. Have you ever been in a situation where the weather completely changed the way the world sounds? Share your story in the comments below. It's a fascinating side of nature we don't often talk about. As if that weren't enough, these chaotic systems can cook up one of meteorology's rarest and most awe-inspiring phenomenon, thundersnow. The same powerful updrafts that create the whiteout conditions can also cause intense friction between ice crystals and water droplets within the squall cloud. This process separates electrical charges, just like in a summer thunderstorm. The result is lightning and thunder in the middle of a snowstorm. Because the snow-filled air dampens the sound, the thunder often comes as a low, muffled rumble rather than a sharp crack. But seeing a flash of lightning illuminate a swirling vortex of snow is a spectacle that few people ever get to witness. What's truly fascinating is that a snow squall behaves like a miniature, self-contained weather system on the march. A strong squall will generate its own leading edge, a gust front, that races out ahead of the snow itself. This is like a tiny, personal cold front that the storm creates and pushes forward. If you're in its path, you'll experience a sudden, sharp drop in temperature and a violent blast of wind before a single snowflake even falls. It's the storm's warning shot, a clear signal that the main event is just seconds behind. This leading edge is often visible as a menacing-looking shelf cloud, a low, horizontal wedge-shaped cloud that looks utterly terrifying on the horizon. Many of the most legendary snow squalls are powered by what's known as the lake effect. But the secret ingredient isn't just the lake, it's the journey. The critical factor is something meteorologists call fetch. This is the distance that a mass of frigid Arctic air travels over the relatively warm waters of a lake. The longer the fetch, the more time the air has to soak up moisture and heat energy from the water below. A long fetch over a body of water like Lake Superior or Lake Ontario can supercharge the air, turning a minor snow shower into a historic, feet-deep squall band. A short fetch might only produce flurries, proving that in the world of snow squalls, the journey truly is more important than the destination. And while we associate this phenomenon with the Great Lakes, it's a mistake to think they have a monopoly on squalls. This process can happen over any sufficiently large body of open water where there's a dramatic temperature difference. The Great Salt Lake in Utah produces powerful lake effect snow. The bays and seas of Japan are famous for it. Even the Atlantic Ocean can generate ocean effect snow squalls for coastal cities, but it goes even further. Squalls can also be purely frontal, exploding along the leading edge of a sharp cold front with no large body of water needed at all, proving that this weather beast can hunt far from its typical habitat. This leads us to the ultimate paradox of the snow squall, its notorious unpredictability. Even with our most advanced Doppler radar and high-resolution computer models, pinpointing the exact location, timing, and intensity of a specific squall band remains one of the greatest challenges in modern forecasting. These bands are incredibly narrow, sometimes only a few miles wide, and can wobble, shift, or suddenly intensify with very little warning. A forecast might predict a squall for a county, but whether it dumps a foot of snow on your town or the one 5 miles to the north can be a meteorological coin toss until it's actually happening. They are a humbling reminder that even in an age of incredible technology, nature can still be wildly, beautifully, and terrifyingly spontaneous. So, we've seen the raw, destructive power of a snow squall, the chaos, the danger, the sheer speed of it all. It begs the question, if these things are so fast and furious, can we even see them coming? The answer is a complex and fascinating yes, but it requires looking at the atmosphere with a very specific set of high-tech eyes. The tools that predict a massive, multi-day blizzard are surprisingly blunt when it comes to spotting these fleeting atmospheric assassins. In fact, one of the biggest challenges in forecasting snow squalls is that they are often born from what's called low-topped convection. This means the clouds that create the squall aren't towering, miles-high thunderheads that weather radar can see from 100 miles away. Instead, they can be incredibly shallow, sometimes only a few thousand feet deep. A standard NEXRAD radar unit scans the sky at different angles, or tilts, starting near the horizon and working its way up. If a squall is far away and very shallow, the lowest radar beam might overshoot it completely, rendering the storm practically invisible until it's almost on top of you. It's the atmospheric equivalent of a submarine running silent, running deep, or in this case, running shallow. This radar invisibility problem is precisely why the development of dual polarization radar was such a monumental leap forward for severe weather prediction, especially for squalls. Before this upgrade, radar could only tell you the size and intensity of precipitation, basically how big the targets are and how many of them there are. But dual pol, as it's called, is far more sophisticated. It sends out radio waves that are polarized both horizontally and vertically. By analyzing the returning signals from both orientations, meteorologists can determine the shape and variety of the objects in the air. A perfectly round, tumbling hailstone will give a very different signal than a flat, fluttering snowflake or a wobbling, oblong raindrop. For snow squalls, this technology is a game changer. Forecasters can watch in real time as rain, driven by a cold front, rapidly transitions to wet, heavy snow. This specific signature, the telltale sign of a flash freeze in the making, is something dual-pol radar can see with astonishing clarity, giving forecasters the confidence to issue a warning for what's about to happen at ground level. But even the most advanced radar has its limits, which is why meteorologists also turn their gaze upward, looking at the storm system from space.
Satellite imagery is absolutely crucial for identifying the larger pattern that spawns a squall. Long before the snow starts to fly, forecasters are scouring satellite loops for the telltale signature of a powerful Arctic cold front. Often, a developing snow squall line will appear as a stunningly clear, narrow, and well-defined band of clouds. This feature is sometimes called a rope cloud due to its long, thin, and winding appearance from above. Seeing this rope cloud on a visible satellite image, especially when it's moving quickly and shows signs of vertical growth, is a massive red flag. It's the visual confirmation that the atmosphere has organized itself in a very specific linear way, creating a perfect runway for a squall to race along. It's like seeing the shadow of the shark before you see the fin. Now, seeing the pattern is one thing, but predicting its formation hours in advance requires a different tool entirely: computer modeling. General weather models, the ones that give you your 5-day forecast, are brilliant for seeing the big picture. They operate on a coarse grid, which means they can't see features as small and fleeting as a snow squall. It's like trying to read fine print with a blurry magnifying glass. This is where specialized, high-resolution mesoscale models come into play. Models like the High-Resolution Rapid Refresh, or HRR, are designed specifically for short-term, small-scale weather. They run on a much finer grid and are updated every single hour, allowing them to ingest the very latest data and simulate the atmosphere in incredible detail. These models are powerful enough to actually predict the initiation of a snow squall line a few hours before it forms, showing forecasters precisely where the lift, moisture, and instability will align to trigger the event. It's the closest thing meteorology has to a crystal ball for these specific threats. Have you ever been caught completely off guard by a sudden weather event that wasn't in the forecast? Let us know about your experience in the comments. While satellites and computer models paint the picture from afar, nothing beats cold, hard data from the ground. That's why surface weather observations are still the bedrock of snow squall forecasting. An automated weather station is a meteorologist's best friend during a high-stakes event. They are looking for a classic, textbook trio of signals that scream Arctic front. First, a sudden, dramatic plunge in temperature. A drop of 10 or 20 degrees Fahrenheit in mere minutes is common. Second, a sharp, decisive wind shift, often with a simultaneous surge in wind speed. The wind might have been out of the south all day, but as the squall hits, it will whip around to the northwest in an instant. And third, a rapid spike in barometric pressure. This indicates the dense, heavy, cold air has arrived and is wedging itself under the warmer air mass. When a forecaster sees this sequence of events on one station, they know the station just down the road is next, allowing them to track the squall's progress with pinpoint accuracy. Because of this unique and severe threat, the entire warning system had to be adapted. For decades, we had winter storm warnings for long-duration events and blizzard warnings for wind-driven snow, but nothing quite fit the profile of a squall. So, in 2018, the National Weather Service introduced a new alert specifically for this phenomenon, the Snow Squall Warning. This isn't just another winter weather advisory. It's treated with the same life-or-death urgency as a tornado warning. The warning is issued for a very small, specific area, often just a county or two, and for a very short duration, typically 30 to 60 minutes. When a snow squall warning is issued, it triggers the wireless emergency alert system, sending a notification directly to every cell phone in the targeted polygon. The goal is to grab the attention of motorists and give them a crucial, albeit brief, window to avoid or exit the highway before visibility plummets to zero. It's a modern solution for a fast-moving, modern transportation problem. Finally, in the age of instant communication, one of the most powerful forecasting tools isn't a satellite or a supercomputer, it's you. Citizen scientists and trained storm spotters are an invaluable part of the warning process.
Because snow squalls are so localized, the official network of weather stations can sometimes miss the worst conditions. A real-time report from a trained spotter on the ground confirming whiteout conditions and icy roads is pure gold for a forecaster. This human intelligence can verify that the squall is behaving as predicted and gives the meteorologist the confidence to continue the warnings for communities downstream. Even public reports on social media, when they can be verified, help to paint a more complete picture of the squall's impact. It creates a feedback loop where technology predicts the threat and human observation confirms its severity, a partnership that is essential for saving lives when minutes or even seconds are all you have. Imagine driving down a clear highway. The sun is out, the road is dry. Then, in the distance, you see it. A churning, menacing wall of white, moving impossibly fast. You have seconds to react before you're swallowed whole. This isn't a scene from a disaster movie. It's a historical reality that has blindsided armies, trapped pioneers, and reshaped our understanding of winter's fury. Today, we journey back in time to uncover the chilling legacy of the snow squall. For as long as humans have contended with winter, these sudden ambushes of snow and wind have been a terrifying, often unnamed force. We often picture the Continental Army at Valley Forge simply enduring a long, brutally cold winter. But the story is more dynamic and far more terrifying than that. Their suffering was punctuated by sudden, ferocious storms that we would now classify as snow squalls. These weren't just blizzards that settled in for days. They were rapid-fire assaults that would dump several inches of snow in under an hour, driven by gale-force winds. These events made logistics a nightmare. A supply wagon that was moving easily one moment could be hopelessly bogged down in a deep drift the next. For the ill-equipped soldiers, a sudden squall meant a rapid plunge in temperature and blinding conditions that could lead to lethal frostbite or getting lost just yards from their own camp. It wasn't just the cold that tested them. It was the sheer, violent unpredictability of the weather itself. This terrifying unpredictability wasn't confined to the battlefield. Fast forward about a century to 1888, a year seared into the memory of the American Great Plains. The infamous Children's Blizzard is a haunting tale, but its deadliness came from its squall-like nature. The day began as unseasonably warm, a welcome thaw in the middle of January. Children went to school in light coats, and farmers were out working their fields. Then, with almost no warning, the sky turned a dark, boiling gray. The temperature plummeted, in some places by nearly 100 degrees Fahrenheit in 24 hours, as an Arctic front slammed down from Canada. What followed were intense, localized bursts of snow so thick and wind-whipped that visibility dropped to zero. It was a classic snow squall scenario on a massive scale. Many of the victims were school children trying to get home, who became disoriented and lost in the whiteout just feet from safety. The storm's speed, not just its cold, is what made it so catastrophically deadly. It's truly sobering to think about how a change in the weather, happening in mere minutes, could alter so many lives. What's the most extreme weather shift you've ever personally experienced? Let me know in the comments. I'm curious to hear your stories. This weaponization of winter by Mother Nature has also played a direct role in human conflict. During World War II, the Battle of the Bulge is remembered for its brutal, freezing conditions. But specific, intense snow squalls were a key tactical factor. In the opening days of the German offensive, a persistent weather pattern prevented the Allies from using their greatest advantage: air superiority. But it was the intermittent snow squalls that made life on the ground a special kind of hell. These were not gentle snowfalls. They were sudden, violent whiteouts that would sweep across the Ardennes forest, reducing visibility to near zero in an instant. Patrols would get lost, firefights would become chaotic, and the simple act of navigation became a life-or-death struggle. The Germans used this disorienting weather as cover for troop movements, while Allied soldiers, particularly those new to the front, found the psychological impact of being suddenly blinded by a wall of snow utterly terrifying. The squalls acted as a neutral, chaotic force, disrupting plans and adding another layer of misery and uncertainty to one of the war's bloodiest battles. While some storms influence battles, others redefine meteorology itself. The Great Appalachian Storm of 1950 was an absolute monster, a cyclone that sprawled across the eastern United States. But within this massive system, it spawned countless intense lake-effect snow squalls that were unlike anything people had ever seen. In cities like Cleveland and Pittsburgh, these squalls were so violent, with winds gusting over 100 miles per hour and snow falling at rates of 5 inches per hour, that people reported them as snow tornadoes. The sheer force of the wind, combined with the blinding snow, created blizzard conditions in an instant, burying entire towns and setting snowfall records that remain untouched to this day. It was this event that truly hammered home how a larger storm system could create localized, hyper-intense weather events that were a unique danger all on their own. And what about those flashes of light and rumbles of thunder during a squall? The phenomenon we call thundersnow feels like a modern discovery, a cool bit of weather trivia. But people have been documenting it for centuries, completely baffled by what they were seeing. You can find historical accounts from as far back as the 18th century, where people describe the profound confusion and even fear of witnessing lightning and hearing thunder while being pelted by heavy snow. They lacked the scientific framework to understand that the same atmospheric instability that creates a summer thunderstorm could, under freezing conditions, produce a snow squall with an electrical charge. To them, it was a deeply unnatural event, a blending of seasons that defied all logic, and it was often recorded as a strange and portentous omen. Sadly, it often takes tragedy to spur change. For all our scientific understanding, the public warning system for snow squalls lagged dangerously behind. A major turning point came from a horrific chain reaction pileup on Interstate 80 in Pennsylvania back in 2014. On a day with otherwise good visibility, a fast-moving but incredibly intense snow squall swept across the highway. In seconds, visibility dropped from miles to feet. Drivers, traveling at full speed, were suddenly plunged into a complete whiteout. The result was a catastrophic 78-vehicle pileup. This event, broadcast in terrifying detail, served as a massive wake-up call to the meteorological community. It tragically demonstrated that our existing warnings for winter weather were not specific enough for the unique flash freeze danger of a squall. This disaster became a direct catalyst for the National Weather Service to develop and implement the Snow Squall Warning, the specific, geographically targeted alert system we have today, designed to give drivers those crucial few minutes of warning. It's incredible how a single event can force an entire system to evolve. Can you think of another example where a specific disaster led to a major improvement in public safety? Share your thoughts below. Long before government agencies and advanced radar, however, there were people who knew the squall's danger intimately. For centuries, sailors on the Great Lakes had a healthy fear and a powerful name for lake-effect snow squalls: white hurricanes. The term perfectly captures the terror these storms held. On a frigid, clear autumn or winter day, a ship could be sailing under blue skies. Then, a dark line would appear on the horizon over the warm lake water. Within minutes, the ship would be engulfed by a storm of hurricane-force winds and blinding snow. But the greatest danger wasn't the wind or waves, it was the ice. The combination of freezing spray and heavy, wet snow would encase the entire vessel in a thick tomb of ice in an astonishingly short amount of time. This added immense weight, making the ship top-heavy and dangerously unstable. Countless ships in the age of sail and even early steam were lost this way, capsizing and sinking in minutes, lost to the sudden, icy fury of the Great Lakes white hurricanes. Their legacy is a stark reminder that understanding this weather phenomenon has always been a matter of survival. Imagine a storm so fast, so furious, that it exists on the very edge of our ability to predict it. A ghost in the atmosphere, born from a perfect collision of cold air and warm water. A fleeting monster that can cause a 30-car pileup and then vanish without a trace. We've journeyed through the intricate world of snow squalls, but now we arrive at the frontier, the place where our knowledge ends and the deepest mysteries begin. Welcome to the final chapter of our deep dive. We've learned that snow squalls are incredibly sensitive to temperature differentials, but here's a paradox that keeps climate scientists up at night. In a warming world, some snow squalls could actually become more ferocious. As global temperatures rise, large bodies of water like the Great Lakes are projected to stay ice-free for longer periods into the winter. This creates a larger, more potent fetch for frigid Arctic air to pass over. The result is a greater temperature and moisture contrast between the air and the water, the very engine of lake effect snow. So while total snowfall might decrease in some regions over decades, the individual squall events that do form could be supercharged, dumping staggering amounts of snow in even shorter bursts. It's a chilling reminder that climate change isn't a simple thermostat dial. It's a complex system of interconnected chaos, where a warmer planet can paradoxically breed more intense winter storms. The classic snow squall recipe involves a large body of water, but meteorology is discovering that the planet has other ways to mimic this effect, leading to a phenomenon known as the brown ocean. Imagine a vast expanse of flat farmland that has just been soaked by heavy autumn rains. The soil is dark, saturated, and holding on to the sun's warmth. Now, picture a blast of cold, dry Arctic air sweeping over this immense, soggy landscape. The warm, moist soil begins to release heat and water vapor into the cold air above it, almost exactly like a lake would. This energy transfer can be so significant that it provides the fuel to generate localized, intense bands of snow. A snow squall born not from a blue ocean, but a brown one. This is a cutting-edge area of research, explaining why surprise squalls can sometimes pop up hundreds of miles from any major lake. And the ingredients for these atmospheric beasts aren't just water and air. Aerosols is adding its own secret spice to the mix. Aerosols. These are tiny particles suspended in the atmosphere from industrial pollution, smoke, or even dust. When these particles drift into the air where a snow squall is forming, they act as cloud condensation nuclei. Think of them as microscopic seeds. Water vapor in the supercooled air needs something to latch onto to form an ice crystal. With more pollution particles available, the cloud can form a much higher number of smaller ice crystals than it would naturally. This can drastically alter the squall's behavior. It might lead to finer, lighter snow, or, in some conditions, it could delay the onset of precipitation, allowing the cloud to grow more vertically and unleash an even more intense, concentrated burst of snow when it finally lets go. We are, in a very real sense, changing the texture and intensity of our storms. Perhaps the most electrifying mystery within a squall is the phenomenon of thundersnow. We associate lightning and thunder with towering summer thunderstorms, not with the comparatively shallow clouds of a winter squall. Yet, it happens. The sheer violence of the air moving within a squall, the rapid upward and downward drafts, can cause ice crystals and supercooled water droplets to collide with incredible frequency. This friction can strip electrons, creating a separation of positive and negative charges within the cloud, just like in a regular thunderstorm. When the charge difference becomes too great, it discharges as a bolt of lightning. The sound, however, is different. The fresh, fluffy snow on the ground acts as a powerful acoustic dampener, so the thunder often sounds like a low, muffled thump or a deep rumble that you feel more than you hear. The exact mechanics of how these relatively small clouds generate so much charge so quickly is still a topic of intense debate. Have you ever experienced the strange, muffled boom of thundersnow? Let us know in the comments below. It's one of nature's rarest shows. To solve these mysteries, meteorologists are turning to a powerful new ally, artificial intelligence. Traditional weather models are built on the laws of physics, running massive calculations to simulate the atmosphere. But they struggle with the rapid, small-scale chaos of a squall. The new frontier is machine learning. Scientists are feeding AI models decades of historical weather data, every satellite image, every radar scan, every ground observation leading up to thousands of past squall events. The AI isn't programmed with physics. It learns to recognize the incredibly subtle, complex patterns that precede a squall, patterns a human might never spot. It's learning the feeling of the atmosphere right before a squall is born. This approach holds the promise of not just forecasting if a squall will happen, but predicting its path and intensity with a precision that could save lives, giving drivers that crucial extra 30 minutes of warning. Ultimately, the greatest challenge in squall prediction lies in a part of the atmosphere we live in but rarely think about: the planetary boundary layer. This is the lowest kilometer or so of the atmosphere, the turbulent, messy layer that is in direct contact with the Earth's surface. It's where friction from hills, forests, and even city buildings churns the air into a chaotic soup. Snow squalls are born, live, and die entirely within this boundary layer. Our global weather models are fantastic at seeing the big picture, the massive jet streams and continental weather fronts, but they struggle to accurately simulate the tiny eddies and turbulent flows within this thin layer. Cracking the code of the planetary boundary layer is the holy grail for short-term forecasting. It's the key to truly understanding not just snow squalls, but everything from how pollution disperses over a city to where the best wind turbine sites are. Stretching our gaze beyond our own world, one has to wonder, could snow squalls exist on other planets? Let's look at Mars. The red planet has an incredibly thin atmosphere, but it has polar ice caps made of both water ice and frozen carbon dioxide. It has weather with dust storms that can engulf the entire planet and faint, wispy clouds of water ice crystals. Scientists have observed what appear to be microbursts of snow falling from these clouds at night. Could a unique set of Martian conditions, perhaps wind blowing off the warmer, sunlit pole over a shaded, colder region, create a rapid, localized squall of carbon dioxide or water ice snow? It's pure speculation, but it forces us to see squalls not as an earthly phenomenon, but as a potential expression of universal atmospheric physics, a weather pattern that could be playing out in ways we can't yet imagine on worlds across our galaxy. And this brings us to our final, most profound truth about the snow squall. It's not just an event, it's a memory. The atmosphere has a memory. The plume of moisture that feeds a squall over Lake Erie might contain water molecules that evaporated from the Pacific Ocean a week earlier, traveled across a continent, and were shaped by the Appalachian Mountains. The Arctic air mass that provides the cold shock is the result of weeks of darkness over the North Pole. Every squall is the culmination of a long and complex story, a chain of atmospheric events stretching across thousands of miles and countless days. It is a fleeting, violent, and beautiful expression of the planet's vast, interconnected climate system, a momentary crystallization of atmospheric history, reminding us that even the most sudden storm is, in fact, an echo of the past. From a single, unique snowflake to the awesome, unpredictable power of a whiteout, the snow squall is a masterclass in atmospheric physics. It's a force of nature that commands our respect and continues to challenge our understanding. If this journey into the heart of the storm has sparked your curiosity, be sure to hit that like button and subscribe for more deep dives into the wonders of our world. Thank you for watching.